3D printing, it features an intertwined stator and coil assembly. But will this truly be the motor of the future? And has artificial intelligence officially surpassed human engineering? The modern electric motor is composed of several different parts: a fixed stator and a moving part called the rotor. Magnetic flux is created between these two components, and this allows for rotational movement of a motor shaft. Not all the motors are the same, and these components can be made of different materials. But usually we measure the efficiency and the power density of a motor. Efficiency is the ratio between power input and output, where density is the amount of power you can output per volume. It's important to know these two measurements because we can achieve very high efficiency in many different types of motors, with synchronous topping out at 97%. However, when it comes to power density, there is great variation between an induction and a permanent magnet motor. The ideal design is to maintain these high efficiencies, but have something that's really lightweight and be able to carry high power densities. Toshiba superconducting motor is a very good example of this, because it's only a couple feet long, yet it can handle megawatts of power. It has exponentially more power density than any other motor out there, yet it requires cryogenic cooling, and it highlights the importance of developing superconductors which can work at higher temperatures. So one can consider material science to be the major challenge of electric motors. If you can develop a material which can control eddy current losses, along with having the ability to be custom profiled in 3D printing with a high power density, then you could have something revolutionary and applicable to electric motors. If you want really high power density and efficiency, then you'll typically have to use a permanent magnet design. And this is problematic because it is the most expensive component of the motor. Naturally, companies are looking at different kinds of designs like the induction motor to get around this problem. The induction motor is inherently cheaper, but there are some problems associated with this kind of design, such as speed control, lower efficiencies at low loads, and poor starting torque. So an induction motor could make sense for driving pumps or compressors, but there would have to be modifications to make this work for electric vehicles. We initially have seen this with the Tesla Sin RM, and now we're starting to see magnet-free designs from ZF and Mali. But the induction motor is really appealing when it comes to software design and additive manufacturing, and now we're starting to see 3D printed copper coils. This was indeed a very intriguing development, because laser powder bed 3D printing would be able to build complex shapes, and this can generate some pretty fascinating magnetic fields. It's also very interesting because now algorithmic engineering can custom make the copper coil designs, and this can now be officially fabricated. There is still the challenge of building the motor core. This component provides structural integrity to all the components, so typically this is made out of an assembly of metal steel laminations. Today, soft magnetic cores may be able to be produced through additive manufacturing. This would allow for more freedom in the geometric design, and in turn this would be able to offer transversal flux, multi-axial, and even spherical motors. Koenigsegg showed us that you can forego the lamination steel process, and they gave us a weird radial kind of axial flux motor that's a bit of a hybrid. It produces 800 horsepower and weighs 86 pounds. SMCs can have the same potential in the fact that they can offer these 3D magnetic flux paths. The copper coils can then be configured a little bit differently, and you can be provided with a very weird motor design. Leap71 released the open source software titled Pico GK. Computational engineering can now design electric motor parts. With the SLAM Solutions machine, it can print a multi-material powder deposition solution. The rotor and housing are printed from steel, yet the coils are made from 3D printed copper. This was a really big deal because now we're starting to see some of the first customized stator coil assemblies. In the future, we could see soft magnetic composite materials incorporated as well. With multiple lasers, scanners, and drums, the machine can actively select the powder for each layer. Soft magnetic composites will work really good in this process because essentially they are electrically non-conductive. And it also makes it possible to include another material for the cooling channels. The main drawback is that there's conductivity loss with the 3D printed copper coil, and this could be fixed with further heat treating. What we do know is that laser-based powder fusion of metallic materials is really suitable to produce complex components, but it may not be economical to produce every electric motor out there. So we definitely know that computational engineering is basically limitless. It's a matter of producing the real object, and thanks to multi-material additive manufacturing, we are starting to see 3D printed motors. And we have to keep reminding ourselves is that it's just a prototype and it hasn't been really tested. So there's a lot of questions still remaining about whether or not this is going to be the future production technique of motor design. But more importantly, I would like to know what you think about all these developments. So please leave a comment, like the video if you enjoyed it, and also make sure to subscribe to my channel.